Yeah, okay.
Okay, let's start.
Let's start. It's been eight minutes in the recording, so
Yeah.
Eldon, you cut out 8 minutes of content, especially because we discussed an assignment question just before this, so cut it out. Okay, let's continue on relations. Let's continue on relations. Meanwhile, probably the audience is gonna be like, oh, if only we could somehow uncut the video and scroll back a little bit, oh, and then they hear their assignment question. Oh, actually, even set this as the final, right? That would be very actually, no, I'm getting ahead of ourselves.
Yeah.
Uh, maybe final's a bit too cruel. I think I'll set it for assignment. Okay. So we talked about relations, which by the way, nothing special, just set of ordered pairs, right? Okay. Um. So since it's ordered, you can imagine how we can actually flip it. Let's call it an inversion. Okay. So if I have a relation R which happens to be a subset of A cross B, then the relation denoted by A inverse just happens to be a subset of B cross A. Okay, so it doesn't get any simpler than that, folks. Pretty much what you do is your new set is why did that happen? Your new set is B comma A, which comes from B cross A, if the original pair that you got was A comma B. Okay, so for example, I guess we'll give an example. So let's say I have R, which happens to relate 1 and 3. It also happens to relate, I don't know, let's say like 4 and 5, I guess. Not very creative example, and 2 and 2. Okay, you're wrong. They advocate for the audience.
Yep.
What is R inverse?
So the first one is 3, 1. 3, comma
Yeah,
1. Yep. Then
yeah,
5, 4. And
yeah.
then 2, 2.
2 2. So it's considered flipping, yeah. It's considered flipping.
Yeah.
I
I
mean,
flipped it. You
yeah,
need to
yeah.
trust me.
Yeah. We flipped it. We flipped it. This two is not the same as this two. I mean, okay, it is. We're kidding. We're kidding. We're kidding. It's the same. It's the same. This is how you flip it. This is how you flip it. Right. So that's relation inversion. Okay. So let's go through our two popular mathematical examples again. The divisibility relation and the congruence relation. Okay. So let's look at D versus D inverse. Right. So remember, D is a relation that relates x and y if x can divide y. Okay. So for example, we can say 210 because 2 divides 10, right? So 210 is in D. What this means is that 10 2 is in D inverse. Yay, right? I don't know why
Yay.
I'm so excited about that, but yay. Um, Now, this isn't just for things that are in the set, it also applies for things that are not in the set, right? So, for example, let's say that I have something like 3 doesn't divide 10, right? So I guess we'll say 310. This is not in D. And for that reason, this means that we know that 10 3 is not in the inverse. Yay. Don't know what else there is to say about it. Let's do one more, right? So the congruence modulo 3 relation, right? So again, the one that relates two items if they share the same divisor when divided by 3, right? So for example, 7 and 16 was our example. It has the same remainder when divided by 3, does it? Yes, it does. Took me a second. I doubted myself. Right? This happens to be in M. Okay, so what this means is that again, just flip it around. 16 and 7 happens to be in M inverse. Right? Wait, why did I say 6 and 27 here? This is a typo. This is a typo. We need to get that. We need to get someone to fix that. Oh wait, hold on. No. So this is true. I see. Okay, for the same reason, since we know that 27 and 6 is in M, right? We also know for a fact this means that 6 and 27 is also in M. Okay. No typo here. No typo here. This is correct. This is correct.
M inverse.
Right?
M, as in the
Hmm.
thing. No worries. I'll just edit for you over here. Okay, there we go.
Yeah.
Yeah.
M inverse. Yeah. So this is the inversion operation. Just take every pair and you flip it. That's what we call
Wait, but I'm
inversion.
thinking, is it true? Cause wait, this is the oh sorry, no, this is the congruence modulo one. Okay.
Congruence modulo. It's
Yeah.
not divisibility.
Yeah.
It
Okay.
doesn't even go for divisibility because like 6 doesn't divide 27.
Right. Okay. All's
Right?
good. All's good.
Yeah. All's good. What was I gonna say about this? I was gonna say something. Not to be confused with your matrix inversion. Yeah, I know you guys are taking linear algebra and calculus as well. Not the same. If I had a nickel for every time invert, like mathematicians and computer scientists properly name their stuff, I would have maybe 10 nickels. But yeah. There's a lot of naming collision out there. It's not the same. Not the same inversion. Um, Okay, so that was relation inversion. Let's now talk about relation composition, which is the scarier one. So we're gonna consider having two relations now. So let's say R is a relation and it happens to be, let's say it relates items from A to items in B. And let's say S is a relation that relates items from B to C, right? So pictorially, A to B, this is R, and from B to C, this is S. Category theory, dun dun dun. Okay, like hopefully y'all don't know what category theory means, but if you do, you probably don't belong in this course. Yeah. Oh, you know it's not gonna make a joke about that.
No,
Okay,
I'm not
fine.
familiar with category theory.
Oh, you're not familiar with category
Yeah.
theory? Okay, good. The thing is, that's very scary. Any of you looking it up on the wiki page, right? If you can understand it, like explain it to me. Anyway. Um, let's keep going. So, I have two relations here. One that relates items from A to B, and one that relates items from B to C. Okay, so we can compose them. So we're gonna write that as R semicolon S. R semicolon S. There is other and another popular notation, which is to say R circle S. This is a circle. But we're gonna use semicolon. Okay. So what is the composition of two relations? I'm so glad we got our student TA to color code this. It makes it very readable. But basically, the intuition is that if A was related to something, like we're calling it B, if there exists a B that A was related to, okay, so if there exists a B that A was related to, and at the same time, for the very same value of B, B was related to C, okay, and the first relation uses R, the second relation uses S, okay, in which case we're gonna call this this is the composition. So I guess we should do a simple example first. Or actually, should we do this example? Does that work? I think we can do this example, right?
Yeah, let's do that.
Uh yeah. Uh let me get rid of this. Okay, there we go. So for example, right? This is bus. I think this is bus 284 if I recall correctly. So I used to live here when I was recording this. So the docs myself. But anyway, right? So I think this is
But
bus
you
two.
no
It's
longer
either
stay
284 or
here, right?
285. I no
Oh,
longer say that. Yeah.
right, so
It's
it's
either bus
fine.
284 or 285. So these are the actual bus stop names, right? So I'm going to say that two bus stops are related if the bus goes from one of these stops to the next one. So for example, from Clementi Interchange, it will go to before blocks 315, 318, and from before blocks 315, 318, it will go to block 306, and from 306 it goes to 376, and from 376 it goes back to Clementi Interchange, right? I also don't know why this is always in undercase and this is in uppercase, but it is what it is. Okay, so if this is our relationship, to do A compose A, right? Which we can do, by the way. There's nothing stopping us from doing this. No math police to arrest me. But if we do A compose A, we're going to relate two bus stops. If from one bus stop, we can find a middleman, if you will, and from that, like I guess I'll call this bus stop X and I'll call this bus stop Y. We will relate X and Y. So in other words, X and Y is in A semicolon A. If we can find some middle bus stop, so I'm going to call it M, such that X is related to M and then M is related to Y. Okay, so let's look at this set here, A semicolon A. Well, from Clementi Interchange, we know that there is exactly one middle bus stop between them, which happens to be before blocks 315 and 318, right? This middleman actually carries the bus to the next stop, which happens to be BLK block 306, right? So for that reason, what's going to happen is that in A compose A, we will say that bus stop Clementi Interchange is related to block 306. Does that kind of make sense?
Mhm. Yeah.
Yeah. If I recall correctly, I could be wrong, but I think the composition operation is actually also used in databases, but I don't know if they call it composition. I could be wrong on this. It could be one of the joins, but I don't quite remember. Like one of the joint operations. If one of you is really studying databases and you actually know about this, like maybe post in the forum. Like this would be interesting. But I don't do databases. I think it's pretty clear by now. Yeah. Right. So for very similar reason, let's say for example, block 376, right? So 376, for example, let's see what it's related to, right? So let's think about this. Also, why is this in lowercase? Anyway, So block 376 is related to, from the first relation, it goes to Clementi interchange. We also know that Clementi interchange goes to before blocks 315 and 318, right? For that reason, block 376 actually goes to before blocks 315 and 318 in A compose A. So you're sort of just like taking one step in one relation and then taking one step in another relation, right? So A compose A is like, it's kind of like you're taking one step in one relation, then taking one step in the other relation. Does that kind of make sense? Maybe this is a bit trippy. I don't know. Like, does that
Yeah,
make
I'm
sense?
just thinking like, is it easier to draw it out as a graph?
Yeah, it probably is, right? So let's do an example. So let's make a different relation. I guess we'll call it B, and maybe B is something like, I don't know. Let's make up some stuff. Like one is related to three, and I guess three is related to what, four, and actually let's make this interesting, right? Three is related to one. Is this interesting? I don't know,
What
but
about like something related to itself? Three related to
okay,
three.
three related to three. Okay, so let's do that, right? Three related to three. Okay, so let's look at what B semicolon B compose B is, right? So in other words, B semicolon B. Okay, so pictorially speaking, I have one. I guess I don't have two for whatever reason. I have three and I have
Oh
four,
no.
right?
Yeah.
Okay. So the original relation B, I could draw some arrows to help us here. I'm gonna say like one arrow three, three arrow four, three arrow one, and three arrow three. So this is the original relation B. Okay, let's look at B compose B. Okay, so B compose B is when you sort of take two steps in, well, you take one step in B, then you take one more step in B, right? So for example, I have my usual 1, 3, and 4. So let's take, like, starting from this element, let's take one step in B, right? So I take one step. I think the only step I can take is go to 3, right? So from 1, I'll go to 3, and then I'm going to take another step, but I actually have two possibilities here. I can either,
You have
from
three
1, I'm starting from
possibilities,
1.
but
Oh, I have three possibilities. You're right. So
right.
I could either take one step back to one. In other words, I go from 1 to 3 back to 1. So this is one possibility. Or I go from 1 to 3 and then 3 back to 3. So this is possible, right? Or I can go from 1 to 3 and then 3 to 4, right? So 1 to 4. Right? You can see why this is tedious, right? Because you now have to try all possibilities, right? So
Yeah,
for
I feel
example,
it's
let's
super error prone. Even like this comes out in my discrete math exam, I'm also not even sure whether I get it correct or not.
yeah,
I just try my best to.
which is why you should use this definition. Jang jang jang. But
Mhm.
okay, you made me do this, so we have to finish it now. Right? So for example, starting from 3, we could take one step in B, like this step, and then take this step again, right? So okay. Or we could take this step and then go to 4. Okay. Or we could take this step and go to 1. Okay. What about 4?
You
What
can't
do you think
really
of,
go
like,
anywhere. Yeah.
you can't go anywhere, right? So you actually just, it like nothing ever happens. So this is the result. So if I write this back, B compose B is 1 related to 1, 1 related to 3, 3 related to 1, 3 related to 3, 3 related to 4. Are we missing anything?
Yeah. There's six
What are we
six
missing?
lines though. Uh, one related to four.
Exactly. 1 related to 4. Oh, that's actually a pretty good sanity check. I didn't think of doing that actually. I already knew the answer, so I didn't count. But yeah, I guess you counted, right? There's
Wait, how do you
1,
know the answer?
2,
Okay,
3.
interesting.
Oh, because I saw this arrow and I didn't write it down.
Uh,
Yeah. Okay, so yeah, you can see how maybe the graph is kind of intuitive on what you're trying to do, but mathematically speaking, what is written in the math is just that if you can find a middleman, then you have a new arrow, right? So I guess let's do this example again, but let's use the middleman analogy. So B compose B, you could also think of it this way. I'm gonna take this, copy paste it here, and I will change its color to, let's say, blue. Maybe green. Rate, sorry.
Okay.
Okay. So what is B compose B? I'm going to use blue here. What is B compose B? Well, think of it this way, right? Let's consider. Wait, let's look between the elements 1, 3, and 4. Okay. So between 1 and 1, is there any middleman? Right? So middleman that brings 1, like 1 will step onto a middleman on the green graph, and then from that middleman goes back to 1 on the red graph.
Uh, how do you see easily though? I mean,
I think the way that I would do it is that I would try to see what 1 can visit to here, then go to this graph and see how I can go back to 1.
ah,
Right?
okay.
So
Yeah, so it's
so I will
3
start
lah.
here.
Yeah.
Yeah, it's 3, right? So I will be able to go here to 3, and then I from here, right, I go to this graph, and then I'll say, oh, okay, from 3 I can go back to 1. So there is a middleman, so I can say 1, right?
Mm-hmm.
How about 1 to 3? Is it possible?
Yeah,
Like, is it possible for me to do this? Basically, that's my question.
yes. Because
So
there's
how
a
will we do
self
that?
loop, you can just like, yeah, abuse it. So 1 to 3, then 3 to 3.
Exactly. So 1 to 3, then from this graph 3 to 3, right?
Yeah.
So this gives you this, right? What about 1 to 4? Is there a middleman from 1 to 4?
There is, right? Yeah, it's
Which is
also
3,
3.
right?
Yeah, because it
Yeah,
goes
yeah.
3 by.
So you take one step in this graph, then you take one step in this graph, right? So it looks like this.
Uh,
And you
no.
can work things out that way. Sorry, yeah?
Yeah, connected 1 to 4.
Yeah, yeah,
Yeah,
yeah,
yeah,
yeah.
yeah.
Yeah, yeah,
Not
yeah.
too much. Yeah. Okay.
But yeah, if you think of it as a middleman, that's exactly what the math is saying, right?
Mm-hmm.
It's like saying, hey, if you can find a middleman where you take one step in the first relation, then take another step in the second relation, then in the composed relation, you're just taking one step. That's basically what's going on here. Make sense?
Yeah. Yeah.
Okay. So I prepared this example last year because I used to go through this portion of green and red line a lot, a lot, a lot, a lot, a lot. Uh, it's fresh on my mind. So let's say that I have two different relations. I'm gonna call one of the I forgot what I called in the notes, but I guess we will call this one E for east west line, and we will call this, what's the other one? N, right?
And
N for north south line. Okay, I honestly just call these green and red line, like a kindergartner, but
I still do that too.
you still do that too?
Yeah,
Oh,
it's
very
the
nice.
green line and the red line. Yeah.
So let's say that E is the relation that relates any two stations along the green line, right? So for example, an example of what is in this relation, let's say Bugis, uh, and I don't know, Tanjong Pagar. Why couldn't I have picked an example that Tanjong Pagar, right? So this is in E because they are on the same line. So it's this relation is just like interesting, I guess, because you can take one train to move within this line, right? You don't have to change trains. Um as I guess another example, technically speaking, it's not in the picture, but I guess, like, like Toa Payoh. And what else is on the red line? Uh
Tokyo, I think, hopefully. I am
wait,
not the AMK.
where?
Ang Mo Kio.
Oh, Ang Mo Kio? Well, it's red, right? So I guess so.
Yeah.
You can tell we really don't go to that portion of Singapore. But this would be an N, right? So what about the composition of E and N, right? So in other words, what kind of pairs do we expect to see in this relation? Okay, so you would pretty much expect to see, for example, something like Tanjong Pagar, and I guess we use Dhoby Ghaut as the example here. Dhoby Ghaut. Uh, in yeah, this would be a pair that exists in the relation E semicolon N, because we're taking one 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 step, which could be multiple stations, but quote unquote, one step on the east west line, and then one step in the north south line. That's the idea, right? So this is an example pairing that you can find in E semicolon N. So I have a question. I have a question.
Yeah.
Can I do the opposite? Can I say Dhobi God uh Tanjong Pagar is in E compose N? Can we do this?
Mm, say no, right? Wait, just
Why
checking.
not?
Yeah, yeah, cannot.
Why not?
Uh, I guess because E compose and you need to start from the green and then go to
Go to red, right?
yeah, go to red.
Yeah, exactly. So Dhobi God is a red line and Tanjong Pagar is on the green line. So you can't do this basically. Yeah. I want to try one more. So I have a question. So what if I asked
Mm-hmm.
what about Raffles Place?
Oh, I like how you're using a neutral color. Okay.
Oh, it's not intentional. I
Oh,
just got lazy to switch colors. I just got lazy to switch
cool,
colors.
cool, cool.
Raffles Place and City Hall.
Uh,
Is this in E compose N?
yeah, I mean this is allowed because Raffles Place is indeed in E and City Hall is indeed in N.
Yes. So
Yeah.
even if they're in both, like the point
Mm-hmm.
is that it's yeah, right. You can probably find a middle guy, right? So you can actually pick anyone, to be honest with you, based on this definition. We could have gone from Raffles Place to Tanjong Pagar actually.
Oh yeah, I
uh
mean we didn't
right,
say to find
technically.
the shortest
And then
path, yeah.
yeah, and then from Tanjong Pagar we can go to City Hall, right? So
Mm-hmm.
like, it's like from Raffles Place to Tanjong Pagar, then from Tanjong Pagar to City Hall, right? Yeah. So technically allowed, right? We're taking a green line, like, journey, and sorry, we're taking a oh wait, we can't do Tanjong Pagar. Oh no, that was a mistake. We can't do that. But we can do
Wait,
can
why
we? No,
not?
we can't wait. Because the first relation is green, but the second relation has to be red.
Oh, the middleman has to be
The middleman has to
in
be somewhere on the red line.
both.
Yeah, it has to be in
Mm.
both, right? So we can do Raffles Place to Raffles Place, and then from Raffles Place to City Hall. I guess that's okay. Yeah. Yeah. That's the middleman, right? Because for
Yeah, yeah.
example, we know that Raffles Place, I'm gonna call it Raf P, but Raf P is in E, and we know that Raf P City Hall is in
And
N. So Raf P to Raf P, and then Raf P to City Hall. So that's E semicolon N, pretty much. Yeah. Oh, nearly made a mistake. Oh, whew. Yeah. Okay, let's keep going. Um, zoom. There you go. Okay. So, um, let's come back from let's take a break from reality and start doing some math. um, okay. So let's go through the divisibility and congruence modular examples, just to be safe, right? So again, I'll give you some examples. So let's just say that we know that 510 happens to be in D because 5 divides 10. We also know that 200 is in D because, well, 10 divides 200, right? Um, then we can actually say, by actually kind of by definition, that um 5 200 is in D semicolon D, actually, because in some sense here 10 is the middleman, right? So maybe let's use a different color so that it really pops. Let's use red. 510 and 10 200, right? Because this is in D as a relation, and this is also in D as a relation, right? So now we can say 5 goes to 10, then like, which is the same 10 as this one, and 10 goes to 200. So 5 200 is in D semicolon D. Does that make sense?
mm-hmm.
Yeah. So it's all about finding middleman. So let's do one more last example before we end. We know, for example, like the sharing remainder relation, right? Congruence modulo 3. We know that 3 27, they both have a remainder of 0 is in M, and 27 51 both have a remainder of 0 is in M. So we can actually say that 351 is actually in M semicolon M, or M compose M, right? Because again, the middleman here is 27. Yeah, that's it.
Hmm.
Any questions?
Uh, nope, don't have.
Okay. Then see you in the next video.
Okay, bye bye.